Hello, community. So great that you are back. Let's talk about the latest AI in biomedical research. And this is defined here by some immense opportunity and a staggering complexity level. We have complex knowledge, specialized software, tons of databases, constantly evolving, dispersed. We have constantly rerun. We have integrate all those resources. And today we have a new publication. And here Princeton University and Stanford University, they kind of develop a new coding paradigm. And I have to tell you, I really like this paper. It provides a complete new, fresh look at this. So let's have a look. STELLA. STELLA is a biomedical AI system, and it is designed around the core principle of a self-evolution. Because you don't want, as a human, to do all those tasks. I mean, we have AI for this, yeah? So STELLA architecture itself is simple. We just have 4 key agents. We have a manager agent, a developer, a code developer agent, a critique agent, and a tool creation agent. And all those agents work here beautifully in concert, and it's orchestrating here complex biomedical tasks. And you know what's nice? We have here the latest model from Gemini 2.5 Pro and Claude 4 Sonnet as here really the core of the agents. So we are not going with some old models, but here really the performance data will be from current models. I love it. And as you see, we have 4 agents, we have 4 LLMs, and of course for coding here we have Claude Sonnet, and for the logical causal part we have Gemini 2.5 Pro. Absolutely agree with this. Now let's have a look. What is the manager doing? He is more or less, or it is more or less responsible for the multi-step reasoning plan given here a task by the human. Let's say it develops the strategy. The developer agent then executes those strategy by generating and running here in a Python environment code, or you have access to computer simulation and you can perform complex bioinformatics analysis and you get a numerical result. And then the critique agent looks at this result here from the code agent and says, this looks good, or this is a result that is completely out of line what we expected, no? It identifies flaws and it provides here an actionable feedback. And I will show you it goes in 2 directions, but this is now great because we have now an iterative problem-solving loop with feedback, and this is what we want. You can think of this if you want to go with reinforcement learning. This kind of is an agent that provides here a reward function back. Yeah? And then we have the tool creation agent, and I love this agent because this can autonomously identify, test, and integrate new tools it finds on the internet or maybe on the intranet of your university in response to the demand of a novel problem. So this is now nice. So what is happening? We have, if you want, yes, 4 LLMs, but it's just 2. So Gemini 2.5 Pro gets the human task and says, okay, I have to develop a multi-step strategy for this. I make my first plan how to solve this. And the beauty is it's not trying to do here all the reasoning itself. It says, listen, I have a lot of tools available. So let's go here to Sonnet here, and they have here a Python tool. And I want to do that some beginning calculations are done now in Python, and let's see what comes back. Python does this calculation, Sonnet codes, like you sit down with cursor or whatever you prefer, and you code it and you get a numerical result of a computer simulation. Now, this is now fed into the critique agent, and this agent now also a Gemini 2.5 Pro with a domain knowledge of biomedical, looks at this and says, interesting what we see here, no? And now we have 2 options, no? The critique model can go back here to Sonnet and say, hey, listen, there's one aspect I would like that you run another code experiment and let's see what comes out. Or the critique agent tells here to, if you want itself, Gemini 2.5 Pro, hey, listen, I found a logical loophole. We have to close this. Or I found that there is here, something we have to define in much more clarity. So both systems can, or the critique can communicate now to both systems and further optimize. And you see we have here multiple loops. But it is also that the Python now, if it runs, and this is a successful tool, Now the system can say, hey, great. So I created now a tool for this particular job that works great. So I have now a particular Python program or whatever you have, C++, whatever you like. And now this is a new tool I created. And let's take this. And together here with Gemini knows how to use this tool. So I have the tool, I have the Python file, I have the knowledge how to integrate this tool, and the knowledge how to use this tool is one step of a multi-step strategy, of a reasoning sequence. So you know what? I built now a very tiny little template where I have, for example, a linear sequence here in the strategy, step 14. Great, I built a tool. This is available here in my memory. Here's the command how to use it. And we can feed this back here to the strategy. And now the strategy knows whenever I see an identical task, I know I already solved it. And this is the beauty. At first, you have a learning configuration. Second, we have tool use that makes sense. You see, if you want, intelligence of this AI system of Gemini 2.5 Pro is not to perform numerical calculation, is not to do a financial analysis. It is not anything at all within the LLM. The LLM is limited to its core task, pattern recognition. All numerical simulations, all the tools that you have in your department at your university, all the computer simulations, they are just tools that you give the AI access to and let it run and let it learn. So here you have now from Princeton and Stanford, the official visualization. So absolutely the same. No? We have here a human input. And then we have here the manager agent as the first step. No? Looks here, says, okay, this is the information that I got. Pre-processing and differential analysis. So I have to identify some genes and some pathways to define here a particular cell state here. Summarization, great. So it has now multiple options, the manager agent. It knows here that it has access to tools, and it knows it has access to a, if you want, developer agent, a code agent that can run numerical simulation if there are any open questions. So let's say it does this. It goes now to Sonnet, to Claude 4 Sonnet, and says, hey, just build a Conda environment, and here you are my biomedical program, my numerical Python files. Run this for some particular data, visualize it, write a report, explain your numerical results, do a cluster analysis, whatever the standard things. No? And then the output is not automatically fed back to the manager, but we have now a critique agent. It looks at this result and says, hey, is this reasonable? What is now really the inside of this result? So you see, great. And we have, of course, here the critique agent here is something also like a Gemini 2.5 Pro. What we have now in the feedback is to say optional, we can have a human expert in the loop that says, okay, so I see what the AI is doing and I can have an opinion. I can guide the AI. Or, and I don't think that a lot of universities have access to this, if you have a completely computerized vet lab, so everything is done by computer only, there's no human research assistant that has to do the chemical experiment or the biomedical experiments. So if everything is computerized, no, you have access then to this infrastructure and you can run validation tests. In any way, you get an evaluated opinion on this particular test result back to the manager agent. And the manager agent can either say, okay, I have a final result. I can communicate this. Or it says, oh, okay, this is just solution 1. Now I go and I look, I know that I need now a second step analysis. And now I go to the tool creation agent and either I search now PubMed or GitHub repos on the net or whatever, or I know that I have a tool available here in my, let's call it, private ocean of tools that I have access to in the department of BioMed or theoretical physics or chemistry or whatever. You get the idea. So either a tool is available or we have here our code agent. I say, hey, little Sonnet, build me a new tool for this very specific task. And then if the tool is checked and validated, you can put it here into your tool ocean. So idea is absolutely beautiful. And as I showed you, if we have tools, great. Then with the new tool, we also build here a new reasoning template. So let's say you already have reasoning templates from your other experiments. And now you just add, hey, for the new tool, this is the tool use instruction, whatever. And this is here the reasoning. And this goes here for those particular topics. So you have now in the memory of here this agent, a new template with a new solution pathway. So you see, easy. Linear sequence of solution, linear sequence here of tool use, create new tools, understand it. Absolutely beautiful. What about the performance data? It looks good. Look, if we have here the humanities last exam here in biomedicine, STELLA outperforms the original Gemini 2.5 Pro. I mean, it is in the core Gemini 2.5 Pro, no? But with this tool use, it really can increase its knowledge performance, its complexity solution performance. Here you have O3, here you have Claude 4 Opus, DeepSeek R1. So it's really nice, but it needs time. It needs computation budget, as you see here. Because those, let's say, 26% accuracy, and here in B, you see also the accuracy now on the y-axis, it needs time, no? It needs to run because it needs to learn itself which tool to use, how to analyze this. And then if you run, you get 26% if you have a computational budget times 9. This is now interesting because, yes, you guessed it, we can use this in test time compute. But you have already an indication, maybe it will plateau out, but we have no real information here in the paper. Yes, you have other benchmarks, but you see, STELLA is really great. It's really here, if you look here, Gemini 2.5 Pro and here, Claude 4 Opus, it's really outperforming here the foundational models here significantly because a clever tool use strategy. This self-evolving is so nice because it starts here with some predefined templates here in the cold start, and then it finds its own new solution, its own new path, and it just stores it in its internal template library. So for each subtask or subtask or whatever you want to call it, you have now a validated multi-step reasoning and tool use performance data for very specific subtask. And this is the nice thing here of this agent. It interacts, if you want, maybe with the real environment, if you have this automized wet lab in your university department, or at least you have here the real world computer simulation, the numerical simulation. So from the interaction with the external world, we get validated multi-step reasoning path that we just store, plus the information how to use specific tools. And this, of course, goes in the memory here of the agent. So a classical system. But it is also self-evolving, because you just on the quotation mark have here search tools like GitHub search or PubMed search or whatever, But giving you access to all this, I don't know how many PubMed GitHub repos we have, let's say 1 million. My goodness, Or in your department at the university, you have the top, 20 numerical computer simulation. How great is this that you now can use them independently as an AI system? Plus, don't forget, you can build new tools for some very specific task where you detect, I have a knowledge gap that I do not have the tools for this gap. Like you as a human biomed student, you sit down at your computer, you think, okay, this is my task. Maybe you go to Cursor, you say, hey Cursor, I have access to all the GitHub repos in the world. Now I have this particular problem, start to code some solution. Let's play with this. Let's go with step 1. But why should you do this as a human? AI can do this. So no need for this, for the human. So this self-evolving capability is, I think, here the prime beauty of this paper. So why should you sit down and code a multi-agent framework? You have to focus on something completely different. And the nice thing is that here the benchmark and here BioMed benchmark, it doubles almost. So it's really working. If you want here again an overview, the framework, 4 easy steps. The workflow begins with the manager agent receives the high-level research goal, uncover the mechanisms of acquired chemotherapy resistance, and propose here a resensitization strategy. Understands the goal, guides by its reasoning experience and its domain knowledge here on BioMed, establishing here a very first draft of a reasoning pathway, kind of a strategic plan to decompose the problem into logical smaller steps, like let's run here expression analysis or identify a keystone gene, and then it assigns here the initial data analysis, the first data analysis task to the development agent. This is our computational workhorse. Creates now a content environment, execute here the analysis script, the analysis data are now available, you run different whatever you need to do, and you pass on the results to the critique agent for some evaluation. Now the critique agent here provides the feedback that you need so much, no? But now it's a very specific, it's not a binary feedback that you have here from a reward +1 or -1. No? It really goes here, it has the domain knowledge here, it is a Gemini 2.5 Pro system, it really has here the biomedical knowledge to tell you, there's some problem. No? So it kind of identifies here this critical capability gap of the current configuration of your 4 agents, and then says, hey, I need help. I need now the tool creation agent to develop a new Python program. And guess what? Has access, of course, to all the tool oceans here that we have, all the models here, but it has also this tool creation agent, the ability to build, test, and validate new, more powerful, let's say Python tools, C++ tools, whatever you have. Yeah? So you see, this is now interesting because you have a self-evolving element in this. And STELLA now moves beyond a simple description to a prediction, identifying now specific factors as the keystone regular, often here the resistance network, and so on. What a nice idea. So we have a dual self-evolving capability. The first step, or the first mechanism, if you want, is here the evolution of its own template library that it creates out of the need. And the second is, of course, here this access here to the tool ocean and the ability to write its own programs. Now, this ocean, if you have a closer look, this is quite a diverse array of computational tools. You have more or less everything from functions for querying established scientific databases to interfaces for leveraging large-scale foundation models. You already have in your, BioMed department an AI that was trained on the last BioMed data of the last 10 years. And you understand, or you have customized analysis tool, numerical computer simulation tools in your department. So access to all of this. And what's really nice, you can do this in test time. You don't have to run real complex and lengthy training time routines. In test time, you have the self-evolving capability. So if you think about the computational budget, means money, and the performance you want to achieve, if you just let it run instead of 1 times to 9 times, the accuracy can really go up, let's say from 52% to 63%. So really see direct the benefit here, given a very specific computer budget, improve in the performance in the test time inference run. Now, at the end of the video, I always give place here to the authors and they tell us, hey, STELLA marks here a critical step toward creating truly autonomous AI scientists that can keep pace with the rapid rate of discovery, and especially in biomedicine, absolutely. While challenges remain in bridging here the gap between the benchmark performance and what you need in a real-world lab application, the ability of an agent to autonomously identify and master new tools lays really the groundwork for systems that can explore novel scientific frontiers. This self-evolving agent like STELLA have the potential to really unlock new avenues of inquiry and fundamentally accelerate the engine of biomed discovery. Now, also at the end, I have some personal note. And at first I would like to say, I really like this paper. Have a look at the paper, read it. And you will say, it's simple. No, we know this more or less. No, this system here of a multi-agent system, but never mind, because what it is more or less also really reflecting here on the agent definition itself. No, we have an LLM core for our agent. Then we have the template library, which is nothing else than the memory. And then we have a wide tool ocean, but this is just tool use for multiple tools. Now, you know, whenever we start a new agent in a new domain, we have this cold start problem. No? It has not yet discovered specialized tools or some reasoning strategies. It's really a cold start. And here STELLA can really help because it can create here new reasoning templates. It can create new tools, and it is a self-learning system. So if you have this as a, I don't know, university department here for BioMed, you just need to run this for your department once. And then with every new student, with every new challenge, with every new task, it just learns and learns and learns and learns. It is a dynamic adaptive system, a learner. But this also means that the role of the humans change a little bit, because if I dare to look here a glimpse into the future, the primary role of the AI developer shifts now, no? Because today, if you're a developer, you build and maintain here domain-specific agents, you build multi-agent system by hand. You have maybe a framework, but you decide, hey, I need this agent and this agent, or maybe you have some templates, no, for 8 agent or 16 agent, whatever, and then all the tools. For the cold start, you as a developer, you have to define here the minimum set of tools. You have to define the access of the tools, MCP protocols, whatever you have, agent or agent. You have to do this manually. But why? Because I think we will shift here to design autonomous learning systems, multi-agent framework that learn autonomously. You just need to sit down at the very beginning, design here the first core of autonomous learning multi-agent frameworks, and you then just let it run and have an evaluation. So this means you, in the very next future, you will build here kind of a self-evolving AI engine. You will not sit down and code multi-agents yourself with your human hands, but you just have to think, how can I code a self-evolving agent that I just needs an impulse to start, cold start, and it's running and learning itself. So you see, AI absolutely fascinating if we look at a very narrow sector of BioMed today. And I think we are moving over there from a pure multi-agent tool use network structure more and more to pure capability building systems that are autonomously learning by themselves, interacting with the environment. And yeah, maybe the environment is sometimes a wet lab in the university, and maybe the environment is just a numerical computer simulation. But it gets feedback, it gets evaluated, and it gets here new ideas how to optimize itself. And you see, I'm avoiding any talk about AGI or Meta is now full of this super intelligence. These are marketing terms. They have no meaning more or less here if you are in science, because what you want your AI system to be a self-learning capability building system that evolves automatically. And this is then kind of an AI assistant that I'm looking forward in my department. I hope you enjoyed this kind of video. If you would like to see more, why not subscribe? And I see you in my next one.